All right, CP Physics students, we are starting chapter 4, and chapter 4 has to do with two-dimensional motion. And in order to be able to solve problems in two-dimensional motion, we have to um, become familiar with vectors. Section 4.1 vectors. What's the objective? I can determine the components of a vector if given the magnitude and direction of the vector, and if given the components of the vector, I can calculate the magnitude and direction. So I have to be able to go back and forth. Now, vectors are, of all the mathematical tools used in your physics books, probably one of the most important tools that you're going to use. It's it's impossible to solve problems in two dimensions, three dimensions, four dimensions, however many dimensions your advanced physics courses in college will be, without being able to resolve vectors. So let's talk about vectors. We've kind of learned a lot about vectors this year so far, but we need to go over them again. What is a vector? Vector is a quantity that has both a magnitude and direction. Okay, here's some examples. You have seen these before. Displacement, we can have a displacement north. We can have a displacement east. We can have a displacement north of east. Velocity has magnitude and direction. Acceleration, force, torque, momentum. All of these things are things that we will learn about in this course. What is a scalar? Scalar is a quantity that only has a magnitude, no direction involved. Here's some examples: speed and time. So let's talk about time for just a second. It doesn't make sense to say that I have 30 minutes north. So direction on scalars doesn't apply. Doesn't make sense to say I have 4 gallons east. Density, money. These are examples of scalars. So scalars have no direction. Now, I want to talk about this word magnitude. Scalar has only a magnitude. What does that word mean? Magnitude. Magnitude is the numerical amount of the quantity. So if you're traveling 60 miles per hour north, the magnitude of your velocity is 60 miles per hour. So we drop the direction. So again, we've learned that speed is just the magnitude of your velocity. All right, so we've learned that vectors have both a magnitude and a direction. Now, how do we represent vectors? We have to learn how to represent vectors. When we indicate a vector on a diagram or a sketch, we will draw an arrow, okay, as seen in the figure below. So I have a whole bunch of arrows here. These represent vectors. The length of the arrow represents the magnitude of the vector, okay? So the longer the arrow, the larger the magnitude, and the direction is represented by the direction of the arrow. Now, I also want to point out if, truthfully, if I want to give a value of, let's say, velocity, and it's a vector, which it is, I should have a little arrow hat above it. That is a vector quantity. Now, we lots of times leave this arrow hat off, but that little arrow represents a vector quantity, okay? All right, so if we take a look at number 1, for each of the following quantities, indicate which is a scalar or a vector. So we'll highlight in blue the scalars, the time it takes you to run, so time is a scalar, your displacement's a vector, your average velocity, and we know speed is a vector. I'm sorry, a scalar. Which ones are vectors? Well, we've learned that displacement is a vector. Vectors have direction, displacement has direction, and velocity has direction. And then what about question 2? Let's look at that one. We want to rank in order of increasing magnitude. So notice they give you a hint. The magnitude of the vector is its length. So the longer, the larger. So we notice that B is the shortest, which is smaller than C, which is smaller than A, which is smaller than D. So if we're looking at magnitude, we're only looking at the length of the vector. I would also like to point out, let's say I have, I'm going to try to draw, this is, we'll call this vector E. Vector E is identical in length of A, and let's assume I've drawn that perfectly parallel to A. A and E are equivalent. Vectors are equal when magnitude and direction is the same. Doesn't matter where it started. So origin and final location doesn't matter. As long as the magnitude and direction are the same, then vectors are equivalent. That's going to maybe pop up again in the future. All right. Vectors are described by their components. So we have an example here of the library. I've started at this location and I want to get to the library. You would potentially if you walk to the library, you would eventually, based on your location, have a displacement of this vector r, okay? So that is the displacement of this person. But you're not going to walk that. You can't walk through, let's say, well, you could, I guess, but let's assume you can't because there's buildings on the block. You would walk 3 blocks. This is west, and 3 blocks north. Now, whether you realize it or not, you have just resolved the displacement vector into its components. The displacement vector is r, and you have actually resolved the vector into its components, okay? So every vector has a component. Has two components or more, depending on what dimension you're in, but in 2 dimensions, each vector has 2 components. So let's talk about that. A person walks 3 blocks west and 3 blocks north to reach its library. We did that by counting the number of blocks. What was the place in the person's displacement? So what they're asking for is the value of r, and that is the actual displacement of the person. I have to be able to describe this in 2 dimensions. So how do I find r? Well, I find r, so here's my triangle. All of these are going to be right triangles. This is 3 blocks, this is 3 blocks. I'll give it a unit of b, and I want to know r. Okay, so what do I have to use? I have to use Pythagorean's theorem, which tells me the hypotenuse squared is equal to the sum of the sides squared. And so I would find that to be c is equal to the square root of 3 squared plus 3 squared, which is going to be equal to 4.24 blocks. Okay, so that is the magnitude, but I'm not done because displacement has magnitude and direction. So that is only a part of the equation or the solution. I have to find the direction. If I actually want to describe a magnitude or a vector quantity, I have to actually give its direction. So how do I find theta? Well, I actually have the opposite side and the adjacent side of theta, opposite and adjacent. What do we know about opposite and adjacent? So if I was doing a problem, I always have to write this out because I always forget. I have to write out SOHCAHTOA. So I see that I have the opposite side and adjacent side. So I'm going to use tangent. I know that tangent of theta is equal to the opposite side divided by the adjacent side. And if I want to find, if I want to find theta, I got to get theta by itself. So I have to take the inverse tangent of both sides. So I will take tangent to the inverse of tangent theta, and then I will take tangent inverse of opposite over adjacent. What happens is the left-hand side of the equation, the inverse tangent of tangent gets rid of the tangent. So now I just have theta, and then I have tangent inverse of opposite over adjacent, which is tangent inverse of 3 over 3. And we will find theta to be equal to 45 degrees. So how I answered the question, what is the person's displacement? It is 4.24 blocks at 25 degrees. And notice 25 degrees where? We were 25 degrees this way. We were 25 degrees north of west, or above the negative x-axis. So this is actually how we answer the question. You'll get more practice at that, I promise. Vector components depend on length and direction. So let's see. In the figure 4.4 below, an object has a displacement, here's my displacement, of 1.5 meters in the direction of 25 degrees north of east. The displacement vector is defined by its length, 1.5, and its direction angle. It's been described. However, this displacement vector can also be described by its components. Notice I can break it down into its components. Its displacement is 1.36 meters in the x direction and 0.634 meters in the y direction, or due north. Okay. How did they determine that? Well, they determined that using SOHCAHTOA. So recall cosine adjacent over hypotenuse, which is equal to, in this case, let's redraw that triangle. Here was my angle, here was R, this is Rx, and this is Ry. So the adjacent side to that theta was Rx, and the hypotenuse is R, and then sine of theta was equal to Ry over R. Okay, so using trig relations, we're just going to prove that those values are the same. Okay, so what did they give me? They gave me this was equal to 1.5 meters, I believe. Let's go double check. And this was 25 degrees. And so what we know is that R, we know that Rx is equal to R times cosine theta, and we know Ry is equal to R sine theta in this particular triangle, and that is 1.5 meters times cosine of 25 degrees, and this will be equal to 1.5 meters times sine of 25 degrees. And so we find that Rx is equal to, and I'll just confirm, 1.5 times cosine 25 equals 1.36 meters. I'll just round to 2 decimals, and then 1.5 times sine of 25, and I got 0.63 meters. Now let's go check our answer. Sure enough, that they went to 3 decimals. Okay, no big deal. All right, so here is my components of that vector. Now, if that is a positive 1.36 meters, that's in the positive direction on the x-axis, and 0.63 meters is a positive direction. I could also say east, and this is north. Okay, so I've given both directions and this magnitude. All right, so notice we have this equation that they've kind of given you. They're not, in this particular text, they're not requiring you to, let's say, use SOHCAHTOA extensively, but they've kind of given you this equation. Do I give you this equation? Yes, I do. So in this class, you'll see that we will have to find the initial velocity in the x and y direction, and I have broken it down for you on your equation sheet. Okay, we have an example problem that I'll work in class, but essentially it's going to use SOHCAHTOA. And then the practice problems today are the assignment. So, all right, guys, I hope that helps. We will continue to use SOHCAHTOA. You'll get better with practice, I promise. Have a great day.